Welcome to the Introduction to Organic Chemistry. Let's start with what organic chemistry is. Now, organic chemistry is the study of carbon compounds. Study of compounds containing carbon. Few things that we should review. Carbon has 4 valence electrons. So when we look at its dot structure, it has 4 dots. So it has a bonding capacity of 4. So it can have up to 4 things single bonded to it. Organic compounds exist as molecules, covalently bonded. So we are seeing a sharing of electrons instead of a transfer of electrons. This is important because it does reflect the properties that they are going to have. So when we start looking at what kind of forces of attraction they would have, most of these are going to have the van der Waals forces. In other words, you're going to see dipoles in some of the molecules that will attract together, or dispersion forces, which is due to the movement of electrons. Now remember, these are the weakest force, dispersion being the weakest, followed by dipoles, which is a little bit stronger. So a lot of these are going to be found as gases. Well, they can be found as gases, liquids, or solids, depending on the size of the molecule. We'll get to that a little bit later. But either way, they are very weak forces. So let's say, obviously, if you have a gas, they have weak forces. A lot of your smaller molecules, such as CH4 or methane, would be considered gases. Now, if the attractions are stronger, you will get a liquid. But remember, the liquids, they will have a high vapor pressure. Remember, high vapor pressure is another indication that they have weak intermolecular forces. So when you have it closed off in a bottle, the pressure will build up inside because it doesn't take a lot of heat energy to go from a liquid to a vapor, and then that pressure will build up. Because of this high vapor pressure, quite often you'll get some strong odors from your organic liquids. Some examples, maybe you are familiar with acetone, which we find in fingernail polish. Remember, ether, a very sweet smelling liquid. At one time was used to knock people out. And then you've got benzene is another one. Now, if you do happen to get a solid, they will have a low melting point. A good example would be butter, or shortening is an organic solid that actually will melt very easily. Typically, you're going to have melting points below 400 degrees Celsius. In terms of all of these, typically they are poor conductors. They're not made up of ions, so when they melt, or if you can get them to dissolve, they won't break apart into ions that can carry electricity. They don't have free-moving electrons, that sea of electrons like metals do. So they're not going to be very good conductors of electricity. Now, as always, there are some exceptions in terms of conductivity. Okay, if you have an inorganic or an organic acid base, or an electrolyte, some kind of organic salt, then they will conduct electricity. They're just not as common. So when we talk about our acids, yes, they will conduct electricity. Not very well, but they can conduct. Sorry, this should be salt. they become electrolytes when they're dissolved. Reactivity. Of course, reactivity will vary depending on what kind of structure you have, but most will ignite. They are flammable. If you heat them without air, they will decompose. Both of these are going to occur because at high temperatures, it's very easy to disrupt the bond. So they are readily reactive. Other types of reactivity will be a little bit different. They'll react, but they'll be a little bit slower. So if we talk about rate of reactivity, again, your acids, bases, and salts are pretty fast. Again, because you can dissolve them and they can break apart into their ions, and then they can collide a lot easier. So these are usually a little bit faster, pretty quick, just like your inorganic materials. However, most organic compounds, let me fix the camera here for a minute, running out of space. So for most, they're going to be very slow because they are covalently bonded. Means you need to break apart the bonds before they can react. Okay. Must break apart the bonds before they react. And typically in a normal collision, if you just have them together and they're colliding, you are not going to have enough energy to break that apart. So that tends to slow that reactivity. All right, next we're going to talk a little bit more about the actual bonding that is occurring. So let's start with, again, go back to carbon itself. So we've got carbon. If we look at its electron configuration, 1s2, 2s2, 2p2. And of course you've got 4 valence electrons. Now, when we would look at this in terms of orbital notations, you'd have 2 in the s, and then you'd have your p orbitals, and you'd have 2 there. Well, carbon, again, we know it has 4 valence electrons, and when we draw those valence electrons, we tend to put 1 on each one. That's because this will go through what we call sp3 hybridization. So what actually happens is this, in nature, is going to do this. 2p, and then you're going to have, so that's why they call it sp3, s, and then you've got your 3 p's. Now, when it does this, these are all equivalent. Okay. They have the same amount of energy. The bonds look identical, so we don't notice any difference when it spreads out like that. Again, this is called sp3 hybridization. So if we take a look at methane, CH4, you're going to, of course, get hydrogen bonding on each side of the carbon, and all of these bonds would be identical. Now, another thing that we need to look at is how these rearrange. So this is still going to follow the VSEPR theory, which means these shared pairs will repel from one another and cause the atoms to spread out as far as possible. And this happens in every single carbon atom. So every carbon can have 4 bonds, and these are the bonds that you're going to see. It's always going to have that tetrahedral shape. Okay, and then you'd have your hydrogen, 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 hydrogen. Now if this were to get bigger, one of these hydrogens could be replaced with a carbon, but still off of that carbon you would still get that tetrahedral shape. Now your organic compounds can be small with 1 carbon, it could have 2 carbons, it could be a giant, it could have 20 plus carbons. But either way, every single carbon will always have 4 bonds. because of the way that these organize, that tetrahedral shape, it allows carbon compounds to actually form more than one type of shape from the same number of atoms. These are what we call isomers. Okay, so if you have an isomer, you're going to have the same molecular composition, but you're going to have a different arrangement, what they call a different structural formula. So let me give you an example. You could have C4H10. Okay, C4H10, again, because they can either be butane, or butyl alcohol, ether alcohol, a bunch of different. Here, why don't we just draw them for you? So the simplest for C4H10 would be to have all the carbons in a straight line. Okay, so there's one bond, one bond, one bond. And then your hydrogens would come in. So each carbon can have 4. So you got 1, 2, 3, and then that's the 4th. That would be hydrogen, hydrogen, hydrogen. Here we'd have hydrogen and hydrogen, and then hydrogen and hydrogen. And notice 1, 2, 3, 4. Always make sure there's 4. That's how we're going to know if we have the right structure. Now double check your count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's one possibility. That's one arrangement. Another possibility, we could go like this. Okay, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is a different structure. They have different properties. They have different names. So this is what we call isomers. Now, the more carbons you have, the more possible isomers you could have. This one is usually called butane, and then a common name for this one would be called isobutane. And I say common name because we're going to learn what they call the IUPAC system of naming in the next set of notes. Since this is an introduction to organic chemistry, we're going to start mainly with just hydrocarbons. If you have a hydrocarbon, that means we have only hydrogen and carbon, like the structures above. These are our most abundant, most abundant sources in nature. Would be petroleum and natural gas. Those are our most common or most abundant sources of hydrocarbon that we're familiar with. Now, you can have two types of hydrocarbons. You can have what we call an open chain. Okay. That's what we have up here. We have open chains. Or you could have a cyclic. Okay. Cyclic means you will get a closed chain or a circle. Oops. Now your open chain can either be straight, like butane, or branched, like our isobutane. Okay. A cyclic structure, if we had 4 carbons, we can go carbon, 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 carbon. You could have something like that. And then, of course, each carbon already has 2 bonds, and so that would give you 2 more bonds available, so it would have 2 hydrogens coming off of each side. So it would not be an isomer of butane because it has a different number of hydrogens. Okay, this actually turns out to be C4, and if you count 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it is not an isomer because it doesn't have the same molecular formula. So remember, that's your molecular formula. These are your structural formulas. Another name for an open chain would be called aliphatic. Okay, aliphatic Oops, you can't see that.